They are used as extremely stable cosmic clocks. And that's at the basis of the use of pulsars for gravitational wave searches.
Hello, and welcome to Physics Chat. Physics Chat is a show where we talk about what it's like to be a modern-day physicist, and we discuss everything from our guest research to what inspired them to pursue a career in science. Vox and Sergi are joining me on the hosting panel, and on today's show we have someone super special. He is a legend at the University of Birmingham, where he is a professor of astrophysics. But most importantly, he was my undergrad tutor, supervisor, and lecturer, so spent 4 years answering my questions. And guess what? He hasn't finished yet because he has decided to be on Physics Chat. Professor Alberto Vecchio, it's great to have you on the show. How are you doing?
I'm fine. Thank you very much for inviting me here. It's a great pleasure to be around.
Oh, thank you so much for being on Physics Chat. I know you're a super busy person, so we're extremely grateful for you taking time out of your schedule to talk with us. So let's delve right in. If you could do any other job other than physics, what would it be and why?
I'd like to be an architect. Of course, the problem is that I wouldn't be a Renzo Piano, but I really like glass, steel, concrete, and, mixing both the sciencey part and the, more creative things, I think would be really phenomenal. But unfortunately, have no talent whatsoever. So that career is already dead.
Yeah, that's a great answer. But unfortunately, for the benefit of physics, you chose to be a physicist, and you have been very successful in your career. So what skills and characteristics have you had to develop in order to be successful in your field?
I think one needs to work hard, be very resilient, and understand that to be successful, whatever this really means, is not necessarily down to sheer brain power and IQ, but is a much broader set of skills. Of course, you need to be, pretty decent at physics, but also there are so many other skills that are involved in it that I think that you need to be a whole-rounded person.
Good to know. We've had many different gravitational wave researchers on this channel. You can see the multiple videos we have. Please, could you tell us about your specific research in this area?
Yeah, I've been working in what is now called gravitational wave astronomy for a very long time. I got into this field when it wasn't gravitational wave astronomy yet. It was an attempt to, putting together these detectors, the LIGO detectors, in order to try to actually observe gravitational waves. So I started, working on sources, developing data analysis methods. I then was part of the group within the LIGO scientific collaborations that developed analysis tools, and eventually was fortunate enough to, put their hands on the very first gravitational wave detection, this binary black hole that we observed in September 2015. And from then on, we started to work about understanding what is the physics and the astrophysics of these sources. So that has been a major part of the work that I've been doing, but LIGO is just one aspect of observing the universe in gravitational waves, and I've been involved in other projects, for example, the LISA project, the space-based instrument that now finally ESA is about to make real in January of this year. Though this is a mission that is for you who are young. I'll probably be dead by the time LISA flies. And I've been working on pulsar timing arrays, therefore using pulsars in order to try to observe the very low frequency gravitational waves. So I'm a mishmash of things. It's hard to define exactly what I've been working on.
That's amazing. That's a lot of different stuff. Some of it the future, some of it the current. Something you mentioned. Could you explain what a pulsar is and why they're used for this particular pulsar timing arrays technique?
Yeah, so pulsars are dead stars, the remnant of supernovae. These are objects that are about the size of a city, about 10 kilometers. They have a mass of about 1.5 times the mass of the sun. So it's an extremely dense and compact object. They are almost entirely made up of neutrons, and they spin extremely rapidly, like several hundreds of times per second. They have a very strong magnetic field, and through this very strong magnetic field, they produce a beam of radio waves that is, because they are rotating, that sweeps the sky once every rotation. So it's a sort of lighthouse. And if we happen to be along the line of sight of this beam, we get hit once per rotation by this beam of radio waves. So this is where the name pulsars comes from. So they are extraordinary objects, and because they are rotating so rapidly and the rotation is extremely stable, for many applications, they are used as extremely stable cosmic clocks. And that's at the basis of the use of pulsars for gravitation wave searches.
Right. So to compare it to the other type of gravitational waves that you said you also worked on, the normal LIGO ones, binary black holes, neutron stars. Yeah, can you explain how that works a bit?
So for LIGO, we'll build an instrument. It's a phenomenal achievement in in applied physics, in engineering, in technology, where we built a detector in order to measure these fluctuations of space and time. But LIGO, because it's a ground-based detector, has optimal sensitivity at about 100 hertz, and in particular is limited at low frequency to about right now 10 hertz, and is not going to be able to observe gravitational waves at frequency lower than about 1 hertz. So, but the gravitational wave spectrum, as the electromagnetic spectrum, is extremely rich, and we have waves across many wavelengths. And one of the very interesting frequency bands that we have in the gravitational wave spectrum is around 1 nanohertz, so 1 billionth of a hertz. So these are very low frequency waves, therefore very long wavelength gravitational waves. For these, if one wants to observe these waves, and one of the reasons is that it could tell us something about supermassive black holes or processes in the early universe, one needs to have a completely different kind of instrument. It needs to be, let's say, space-based. So the ingenuity has been that one could use this pulsars, these very stable clocks, to effectively assemble a galactic scale gravitational wave detectors. So we time these pulsars. These pulsars are extremely precise clocks. Let's assume they are perfect clocks. So we would get 1 pulse of radio waves every rotation. If there are gravitational waves at these very low frequencies, then the arrival time of these pulses would not be so regular, but would be a little bit earlier, a little bit later, by a tiny amount, which is determined by whatever other gravitational waves. So this is the way in which we are using a cosmic object, a pulsar, in order to study some other cosmic phenomena.
Right. So this must be a massive effort to make this possible. Can you tell us about how this happened in practice? Who were the people behind it?
Yeah. So as I said, there are these pulsars. We know about 2,000 of them. However, these are not perfectly stable clocks. So we need to find those that are particularly stable and then observe them very regularly, once a week. And do this for literally years, because if we want to reach frequencies that are as low as 1 nanohertz, then we need to observe these objects for several years, tens of years. So over the last really 2 decades, radio astronomers around the world have started a program really to time regularly about 100 of these pulsars using several telescopes around the globe, so the very best radio telescopes have been having these timing program of these pulsars. So this requires a large effort in terms of telescope time and people, and so several collaborations have been established to do this. I'm part of the European pulsar timing array collaborations that is using telescopes in the UK, in Germany, in France. There is the North American collaboration, Nanograv. There is the Australian collaboration, and now there are more and more people around the world who are joining this effort under an umbrella that we call the International Pulsar Timing Array. Really, you need a concerted effort in order to try to do something that people think is close to being possible.
Amazing. That's, yeah, so many people, so much time just to get this sort of singular measurement.
Oh, absolutely. Absolutely.
Yeah, truly amazing what we can accomplish when we actually try to work together for once. So why, you mentioned nanohertz, and we've talked about why this is particularly different to other gravitational waves. So what's interesting about this frequency of gravitational waves that you might not measure in the other detectors?
Yeah, so there are two key targets, if you want, plus of course a large discovery space, because we are observing the universe, because we are not quite sure what's out there. So who knows what we're going to discover. But one of the key motivation to do these pulsar timing array observations is that we know galaxies have massive black holes at their center, like our own Milky Way. We also know that galaxies merge together through cosmic times. And through this merger of galaxies, we think that each of the galaxies that merge would bring a massive black hole at the center of the newly formed galaxy. And these black holes would form a binary system, spiral around each other, and then radiate gravitational waves. So these are the kind of gravitational waves that would emit at these very low frequencies. So if we could observe gravitational waves from these massive black hole binaries at the center of galaxies, then we would have a view of how these large structures assembled. And on the other side, we know that the early universe produced a background of gravitational waves in the very same way as we have a background of photons for the cosmic microwave background. That has never been observed. We do not quite know what is the physics. Let's give it a go. We might see something, and that would be extraordinary.
So Alberto, now it's time for my favorite part of the show. It's the random question. So if you could have dinner with a celebrity, who would you choose and why?
Oh, a celebrity.
Do you know any?
Of course.
Okay.
I get invited all the time. That's the problem I have here. Okay. That I, have lunch and dinner with them all the time.
Oh,
so
sorry.
I know how boring they are. And I'm trying to find who's the celebrity that I haven't met yet that I would talk to. Chris Wellington. You don't even know who she is. You don't even know. Probably she's not a celebrity. Okay. So she's someone who won the Ironman triathlon, I think 4 times. She's run 13 races and she's won all of them. And then she retired. So I would be interested to talk to Chris Wellington.
Amazing.
I think that's her name. Is Chris her first name? I think. Chrissy Wellington. I should Google her. Let's see.
You know her very well.
Chrissy Wellington. It's called Chrissy Wellington. Okay. Yeah. So I always wanted to run an Ironman, but my body's falling apart. So I think that's not on the cards anymore.
Okay, so you would like to go for dinner with her because she's a runner and get advice from her?
Absolutely. I mean, doing the Ironman is really tough. Okay. And really, really tough. and also doing it and just win. I mean, you just win. Every time you show up at the start line, you only win. Okay, so that's remarkable. I never won anything. Okay, if I show up at the start line, I only lose. So that may be down to talent, but I suspect there is something different. So I'm sure it would be an interesting conversation.
Sounds good. Maybe we'll have to set this one up. What about you, Sergi?
Okay, if I could pick someone who's dead, I think I would love to have a dinner with Plato. I think going to one of these symposiums where they met with friends and they drank wine and ate food while talking about anything, I would love that very much. I think the language might be a barrier, but I don't know. Yeah, this is a magical scenario, so that's not a problem.
Nice. If I could have a meal with a celebrity, I think it would have to be Kim Kardashian because I love her outfits.
I think that would be an interesting dinner.
That would be a very interesting dinner. I'd love to ask her about her business adventures as well. So yeah, Kim, if you're out there, let me know. Right.
Sounds great. So the use of these pulsar timing arrays has already produced some very nice results, but we're only at the start of this. So what are we hoping to observe in the next decade? How is this going to improve in the future?
So the first step, I think, what we would like to try to do in the next few years is really to, follow up the observation that we've done so far and put on a very strong statistical footing this result of this evidence of a background. So with that one, hopefully out of the way in the not too distant future, then going back to what we were discussing before, we would like to try to understand whether there are signatures in this background, for example, anisotropy, or to measure the spectrum that would allow us to actually use what we observe in order to learn new physics. The population of binary black hole, massive binary black holes, or phenomena in the early universe. And then, of course, what we really would like is at some point to identify an actual binary of two supermassive black holes in a galaxy which is not too distant. And I think that would be pretty fantastic because that would also be a target for observations with a number of other facilities, other telescopes, to try to understand and study this source, because this would be a super first, and I'm sure a lot of telescope time would be spent to try to understand that system. But we are dreaming a bit, so we'll go through the motion slowly.
I think we've lost Fox. So what I think the plan will be, we've asked all the questions. That's perfect. So what I was thinking, but maybe you could wrap things off for us by just reading.
That's fun. Yeah, that's good.
Just so
I need to read?
Yeah, you'll read.
Thank you so much. But I'm a terrible actor. I really can't do these things. I don't know how they do it. Thank you so much for being on Physics Chat and for explaining pulsar timing arrays. Who knew there were other ways to detect gravitational waves? Let us know in the chat. Let us know in the comment section if you could have dinner with a celebrity. Who would you choose? Why? We look forward to hearing from you. So keep writing. From everyone at Field of View, we hope you have an amazing day, and goodbye.
Bye.
Bye.
Okay, very good. We do not quite know what is the physics. Let's give it a go.
Yeah, if it had to be someone who's alive, maybe Messi would be good. But
come on, Messi. No, Messi. Oh,
yeah,
just because you can play football. Where are you from?
I'm from Barcelona, so big Messi fan. Yeah, I think maybe I would enjoy more the conversation with Plato, but I mean, being with Messi would be such a privilege that, yeah, I would just stare at him.
Great conversations
But
then.
always the magician, not the central midfielder who keeps the team in check and actually who's the guy or that runs the show. So that I have a real problem with this.
Yeah, no, I get that. Yeah, maybe I can invite Iniesta and Xavi.
Exactly. You see?
Yeah.
Without those, Messi, if you just leave Messi there with me and a few others, he would not be that successful. So
no, definitely
I think we should really give credit to the others. But anyway.